All right, let's put some numbers on that example. So with our formula in hand for the rise h, we can see what kind of rises we can expect to find. So if we look up the value of the surface tension of a water-air interface, it turns out that at room temperature that's about 73 millinewtons per meter. Let me just say a little bit of a word about surface tension. So there is an appendix in the back of the book that has some values for some liquids. Interestingly enough, water is not listed there, but you can find it almost anywhere on the internet. So the most common value for water is that 73 millinewtons per meter that I'm quoting. But so water in general turns out to have one of the higher surface tensions of any liquid. And the reason why is basically because if you think about where surface tension comes from, it comes from basically strong bonding between the molecules that are involved. So polar solvents tend to have stronger values of surface tension than other things. So water's almost at the top of that list. Other polar solvents are up there too. And then about a factor of 4 beneath those are the non-polar solvents, things like hexane or weakly polar things that are part of like large molecules. So anyway, you can consult Engineering Toolbox if you want to see some other values. The largest value for surface tension that I'm aware of is for mercury, so a liquid metal. And the reason is obvious. It's because metal molecules try and bond very strongly to one another. So whenever you have an interface where like they can't bond very strongly with the air, say, that's a big energy penalty for a liquid metal. So liquid metals like mercury are a big penalty. There's some other liquid metal type materials out there, but that's the primary one. Okay, so the next quantity on my list here is the contact angle. So as I mentioned, contact angle is usually measured by experiment, but water generally strongly bonds to materials like glass or metals. So glass, for example, the contact angle is it's a small number. It's very close to zero. The cosine of theta is not super strongly dependent on theta for values of theta near zero. So making the approximation that it's zero is actually a pretty good approximation. And the density of water is 1,000 kilograms per meter cubed. And I guess for this example, I get to choose whatever diameter I want. So I'm going to choose a diameter that emphasizes the effect of capillarity. So I'll choose something. Generally, it turns out that pores that are underneath about 1 or 2 millimeters in size generally have large capillary effects. So I'm going to choose one randomly that has a diameter of 0.6 millimeters. And if you plug in the numbers based on that, you'll see that the expected rise is about 4.9 centimeters if we use our formula. But so just thinking back, the key things, if you want to use surface tension or capillarity as a tool to do things, you're looking for situations with large surface tension, situations with where the solid is very strongly attracted to the liquid so that you get a low contact angle for maximum force. And you're looking for the smallest pores that you can get, right? So it's inversely proportional to pore size. So if you're looking to draw stuff up, you want to have small pore sizes. So those are basically the 3 factors that matter.